Um, we, with all the days that have been canceled and stuff, we are a little bit behind, and I'm going to make up some of that time on linear momentum stuff. Um, we're going to skip a few of the problems or parts of some of the problems. Um, and I'm not going to go into detail on some of the things I normally do. I don't think you'll miss it in later classes or anything. Um, but okay, back to linear momentum. Yeah, we should just have like a party, like get those bags where everyone gives each other candy and play music and stuff. That'd teach people to skip class. Okay, back to linear momentum. Um, so there are two results that we're going to use. Um, the first one says that the change in linear momentum is equal to the integral from instant 1 to instant 2 of um, the net force vector dt. Um, it's important to notice that this is an integral with respect to time, because later we're also going to do integrals of forces with respect to a distance along an axis. Okay, so it's going to look very much like this, but you're just integrating with respect to a different variable, and it's going to be a totally different quantity that we'll use in other ways. And then the other result, so this is the momentum equation, impulse. And then the second one is uh, if F net is equal to 0, then the total momentum of your system at instant 1 is equal to the total momentum of your system at instant 2. That's conservation of linear momentum. And we started a problem last time. Now we'll go through it. Um, so, yeah, no problem. Okay, so this example that we started last time was a baseball comes in, and I'll give you the angles and the speeds and stuff, and then it gets hit by a bat. We know the duration of the contact. You could tell that from like a high-speed video or something. And from a high-speed video, you can measure the velocity before the collision starts and after the collision ends. And then if you know the mass of the ball, that's enough for you to figure out what the average contact force is, basically. Okay, so that's often a very useful thing. By the way, uh, these are always used in collisions, impacts, and explosions. There really are not many applications outside of those things. So like as we go on and we learn more techniques, more physics approaches to problems, it can be a little bit of a challenge to figure out, okay, all these numbers and things are thrown at you. What technique am I using here? Well, this is the answer here. So if you remember this, you'll always know when to use a linear momentum approach. Yep. Um, it, the conservation of linear momentum is the one that uh, probably are applications to the first one, but I'm not really sure what it is. But conservation of linear momentum is really useful with explosions. because um, an explosion is all internal forces, so there's no net force acting on the object. And so if this thing explodes and you can measure the momentums of the pieces after the explosion, you know, or some of the pieces, you can figure out the momentum of the other piece or something. Yeah, so the system is the what it originally started as, and then instant two, you're talking about these four chunks that are flying off or something. Yep. Mhm. Yeah. They're sort of the same thing, I guess. I'm including impacts in there to include things like bouncing off the ground or a wall or something. We don't sort of naturally think of that as a collision between two objects because the wall doesn't really move at all, at least in our calculations. So that's an impact between the thing that you're calculating and then the thing that's basically at rest. Yeah, where the masses of both of them and an impact. I don't know. I just made these terms up, but an impact, I'm thinking of one thing that you're measuring the mass of and one thing you're just assuming just stays there. Like when you land on the ground, it really is a collision between you and the earth, but the earth moves so little that you don't really include that in your calculation. Okay, so our example says, um, so here's a bat. It's swinging this way. The ball's coming in this way. Um, and then pow. And then after the collision, you know, the ball has a different velocity, and we want to figure out um, so we want to figure out the average force applied to the ball by the bat. So before the collision, we'll say that the ball has a velocity vector of 40 meters per second, 5 degrees below horizontal. And after the collision, it's moving at 50 meters per second, 30 degrees above horizontal. And we'll use the mass of a baseball. It's really 0.145 is the required mass of a baseball, but let's say that the mass is 0.1 kilograms. And we want to know what's the average contact force applied to the ball assuming that contact force is much larger than the weight. It wouldn't be that hard to include the weight in there, but you can imagine over this very short duration of contact, like if the ball was a person worrying about its health, it would be very unconcerned with the force applied by gravity. And over that 0.01 seconds, it would be very concerned with the force being applied by the bat. And this impact takes 0.01 seconds. Okay, so the first thing we have to do is figure out, well, we're going to use the impulse momentum equation that says the change in linear momentum is equal to the integral of f net dt. And this really useful fact that we're going to use is if you're only concerned with the average force, because that net force is going to change, you know, at the first instant of contact, it's not going to be a very large force. And then as the ball compresses, that force is going to get bigger. And then as it starts to leave, it's going to get smaller again. But we're just going to assume that it's constant the whole time with a value of F average. And then this is just equal to the average force times, you know, T2 minus T1. And this is just the elapsed time. Okay, so at instant 1, the momentum is, our coordinate system is like this. The velocity vector is 5 degrees below the horizontal, and the magnitude is 40 meters per second. So you can think of that as that velocity vector is 40 times cosine and sine of 185. Yes. Can someone plug that into a calculator and tell me what that is? I think it is now, yeah. Okay. Okay. And so, yep. And the linear momentum is just that times the mass. And so that's just equal to negative 0.3905, negative 0.0348. And the units are kilogram meters per second.
It's 0.1.
Mass, thank you. Yes. So this is negative 3.905 and negative 0.348. Yes. It, I don't think I can really help you that much. I think, I mean, you can remember what the units are just by the definition of the thing, you know, because you're just multiplying a mass times the velocity. And kilogram meters per second, the best I can say is like, if you think of intuitively what momentum means, you think of it as like big fast things have a lot, small slow things have a little, then that's about the best I can do. That was your idea, right? The squiggly under squiggle on the, yeah. I'm going to do that to differentiate momentum from position, but I've never done that before. You don't have to do it, but the thing is, you just have to be careful because now we have a vector quantity called position and a vector quantity called momentum, and they're totally different, and they have the same, they're represented the same. Okay, so that's the momentum at instant 1. And then at instant 2, our velocity vector is 50 meters per second. The angle here is 30 degrees. And so the velocity vector at instant 2 is 50 times cosine and sine of 30. And that is 43.3 and 25. And then the momentum at instant 2 is the mass, 0.1, times the velocity at 2. And so you get 4.33, 2.5. And now the impulse momentum equation says 4.33, 2.5, the momentum at instant 2, minus the momentum at instant 1, which is negative 3.905, negative 0.348. Is equal to the average net force times the elapsed time, which is 1 seconds. Okay, so what's 4.33 plus 3.905? 8.28. And then what's 2.5? Well, I can do that one. And then the I component is 2.85. And then I'll multiply that by 0.01. Nope, sorry, divide by 0.01 seconds. 0.1 is the mass, and 0.01 is the elapsed time. And this is equal to average net force. And so that's 828 newtons in the x direction and 285 newtons in the y direction. Okay, this is the average net force. But if you think about, what's the force applied by the weight on this ball? It's 9.81 times 0.1, so 0.9 something newtons. And so we're just, not even going to bother in this case with subtracting that off, but it's not hard to subtract it off if you want to. It just takes 1 newton away in the y direction. Or I suppose adds 1 newton in this case.
How you get the 0.01?
That was given.
Okay. Oh, yes.
Can you explain a little bit, like quickly, the impulse momentum equation?
Yeah, that's the one that says the change in the linear momentum is equal to the time integral of the net force. And if instead of trying to figure out the whole shape of the net force, you're just trying to figure out the average net force, then the change in linear momentum is equal to the average force times the elapsed time. And so that's what we did, was just put all those values in there. On the ball. Yep. Because the momentum, the mass that we used was 0.01. And we didn't know we didn't know the velocity of the bat. So you have to know the momentum of your system before and after the collision. So our system had to be the ball. That's what we knew the velocity of, and that's what we knew the mass of. Yep, that's right. Yeah, it would be really hard to do it with the bat. So, I mean, you can, I think, see the usefulness of that if you're trying to figure out, there's going to be this impact in whatever system you're designing, and you need sort of a ballpark figure for what that impact force is going to be. You can calculate that just from um, measuring the velocities before and after. Um, and by the way, I did this with assuming a constant net force, F average. But you could assume any shape you want and match your results to that shape. You could assume that the force is going to ramp up from 0 at the beginning and end of the interval to a maximum in the middle, and you could fit the rules for the area of a triangle to it. I'm not going to go through that, but if you, it would probably take maybe an hour, maybe 2 or something, but you have the ability to, think through that if you were interested, which I'm not implying that you should be, but it's not hard. Because so this is the impulse momentum equation, and we're trying to isolate this, so I'm just dividing both sides of the equation by 0.01.
That gives you that. The left side gives you the average, right?
The left side is the change in linear momentum.
Okay.
We calculated that, and then we divided by 0.01 to isolate the average force.
But wait, where does the one? I don't see the one in there.
What one?
It adds up on the left side, but when you divide it by 0.01, how do you get divided by 1?
No, multiplying by 1 over 0.01 is the same as dividing by 0.01. All right, so now let's talk about conservation of linear momentum. If the net force on the system is 0 over the time interval from T1 to T2, then the momentum of the system at instant T1 is equal to the momentum of the system at T2. So for example, let's say that you have like a train car coming in this way. Let's say it has a mass of 5,000 kilograms and it's moving at 1 meter per second, and it collides with a second train car that has a mass of 10,000 kilograms and is moving the other direction at 1 meter per second. what can we say about the velocities after the collision? Okay. Well, if these are going up to the instant of the collision, these are moving with a constant velocity. We know they're not turning or anything. Okay. So as long as the speed is constant, then there's no net force on that object between the instant right before the collision and the instant right after. Okay, so we'll make our T1 will be the instant right before the collision. And our instant T2 will be the instant right after the collision. Okay. F net on the system of two cars is 0. You know, anything that's moving with a constant velocity has a net force of 0 because the acceleration is 0. And so we'll calculate the linear momentum before the collision. And that is, so the left cart has a mass of 5,000 kilograms and a velocity vector of, that's in the positive x direction, so 1, 0, right? So 5,000 kilograms times 1, 0. And the second car has a mass of 10,000 kilograms and a velocity of negative 1, 0. Stop me if you have questions. And so if you add those up in the x direction, you have 5,000 minus 10,000. So minus 5,000, 0 kilogram meters per second. Okay. And after the collision, we're trying to figure out what those velocities are. They're not given. So all we know is that the left train car has a mass of 5,000 and a velocity that we'll say, I'll call this V10. And the second car has a mass of 10,000 and a velocity of V20. And so you just get an answer of 5,000 V1 plus 10,000 V2, and then 0 for Y. So conservation of linear momentum gives us two equations. The X equation says negative 5,000 is equal to 5,000 V1 plus 10,000 V2. Y equation just says 0 equals 0, so that doesn't help. So can we solve the X equation to figure out the velocities of the two cars after the collision? No, we have one equation for two unknowns. We can't solve for the velocities after the collision, although we do have some information there. WTF? So what's the deal with that? The deal is, if you think about a collision, just intuitively, like if someone told you, okay, these two objects with a certain mass and a certain velocity are going to slam into each other, where are they going to go? You'd picture it, and then you'd say, well, I need to know more about what the objects are. You know, are they super balls? Because then they would bounce apart. You know, are they Play-Doh? Because then they would stick together. You know, and so conservation of linear momentum is never enough information. It's never enough on its own to determine the motion after the collision. You always need information about the nature of the collision. And then the collision will give you extra equations so you can solve this system of variables. The most common types of collision, the most common simple types of collision that you use in mathematical modeling like this. So two common collision types. The first one is perfectly plastic. And that means that after the collision, the objects stick together. And so that means that the object V1, the object 1, its velocity is equal to the velocity of V2 because they're moving as a single unit. And notice that would be enough information to figure out what these train cars do. If V1 is equal to V2, then what we have here is just 15,000 V. You can think of it like that, We've reduced it to a single variable, and then we can solve for what that combined velocity is. Okay, you with me on that? And then the other pretty common type is perfectly elastic. And perfectly elastic means no energy is lost in the collision. And for that to happen, the objects have to bounce apart. Okay, so the word perfectly in both of these should make you a little suspicious about the accuracy of these modeling approaches. Um, in truth, neither of these represent any physical collisions, but the idea is that you pick one extreme or the other to sort of make your guess at what the velocities are going to be. Okay, so let's do this problem again, assuming that those train cars link together. So let's continue the example above. Assuming that when they collide, the cars link together. So which one of these two cases would that be? Yep. All right, well, we know we have this equation that says negative 5,000 is equal to 5,000 V1 plus 10,000 V2. Now we'll just say that V1 is equal to V2. We'll just call it V. That's the velocity of the thing after the collision. And so our equation gives negative 5,000 is equal to 15,000 V. And so V is equal to negative 0.3 repeating meters per second. And now you can plug that back into the velocity vectors. And we assumed that these are going to be moving along the x-axis. So now we know they're going to be moving in the negative x direction with a magnitude of 0.3 repeating meters per second.
How do we know?
Yeah, I mean, we just have this equation. Once we get to this equation that says negative 5,000 is equal to 15,000 V, just solve for V. Now, we're not going to do any problems with perfectly elastic collisions, but it's not conceptually hard. It's a little more tedious. Um, um, so add up 1/2 times the mass times the speed squared for every object in the system at instant 1. And then that has to equal the sum of the same thing, 1/2 times the mass times the speed squared for every object in the system at instant 2. Okay, that's a messier equation, but it's still another equation that doesn't introduce any new variables, and so it lets you solve the system. Okay. Yeah. Yeah. So right. So our x equation gave us negative 5,000 is equal to this stuff, We set V1 and V2 equal to each other, and then we just solve. It's just algebra. Yep. But yes, that's good intuition. The reason that it happens physically is because they were going the same velocities, and the one going in the negative x direction was heavier. Yep. Any questions about the idea of elastic? I'm going to do one quick example of elastic. So let's say that you have two balls hanging from strings. And they both have a mass m. And let's say this one's coming in with a speed, I'll call it v, and it collides with the other one. In a perfectly elastic collision, what are the ball's velocities immediately after the collision? Okay, well,
What is the velocities?
immediately after the collision. Well, first I'm going to use conservation of linear momentum. At instant 1, right before they hit, this one is going to have a horizontal velocity, right? This one has no velocity, it's just sitting there at rest. And so the momentums of these are mass times v0, that's the momentum of the first one, plus mass times 0, 0, that has no momentum. And so after the, so the sum of those two linear momentums is just mv for the x component, 0 for the y component. Any questions about that? And then at instant 2, we don't know the velocities of either of those two, so it's going to be, they are both going to be horizontal since they're at the bottom of that circular motion. Okay, their velocities are both going to be tangent to the circular path, and so we're going to have the mass times the speed of the first one, or the velocity component, I guess, of the first one, plus the mass of the velocity component of the second one. And so we can write that as mv1, that's mv2, and then 0 for y. So conservation of linear momentum gives one useful equation that says m times the velocity component before the collision is equal to m v1 plus m v2. Okay. Can we solve that? Well, what are the constants and what are the variables? Our constants are m and v. We're trying to solve for v1 and v2, so that's one equation for two variables. We can't solve it. So now we go to the requirement on the kinetic energy, the 1/2 mv squared. So the elastic collision, the elastic condition, sorry. So the kinetic energy before the collision is 1/2 times the mass times the speed squared of the first ball plus 1/2 times the mass times the speed squared of the second ball before the collision. What's that? 0, yep. And so you just get a total kinetic energy before the collision of 1/2 mv squared. And now after the collision, this is before the collision, so that's the v, that's the speed of it coming in before the collision. Okay. So now the kinetic energy after the collision that's going to be 1/2 times the mass of the first one times its speed squared, v1 squared, plus 1/2 times the mass of the second one times its speed squared. Okay, so v is the horizontal velocity before the collision. v1 and v2 are the horizontal velocities of each of the two balls after the collision. Okay, so now our elastic requirement says that this kinetic energy before the collision has to equal the kinetic energy after. So our second equation says 1/2 mv squared is equal to 1/2 mv1 squared plus 1/2 mv2 squared. I might as well divide out a bunch of stuff. Divide everything by 1/2, divide everything by m. And we get our second equation that says v squared is equal to v1 squared plus v2 squared. And notice that we're done with the physics now. All we're doing is solving this system of two equations for two variables. It's still tedious. I'm not saying it, but it's all stuff that at this point you can figure out how to do. I guess I can divide these out too. And let's see. I'm going to write v1 as equal to v minus v2. Yep. V minus v2. And then I'm going to square both sides. So v1 squared is equal to v squared minus 2v v2 plus v2 squared. And then I'm going to substitute it into this equation 2. And I get v squared is equal to v squared minus 2v v2 plus v2 squared plus another V2 squared. These cancel. And you get that 0 is equal to V2 if you cancel those 2's out, and then times the quantity V minus V2. So the solutions are V2 is equal to 0 or V. Well, 0 is what the speed, the velocity of that second mass is before the collision. So we'll ignore that one. And so this is the one we want. And then you can plug that back in and solve for the speed of the first one. What we get is V1 is equal to 0, V2 is equal to V, and notice what this says. If you look at original setup, it says if this first one comes in with a speed of V and these two have the same mass, when they collide, this one is going to stop dead and this one is going to take off with a speed of V. Okay, and so this is like the first chunk in those, those executive ball bouncer things that. Well, they go for a long time because they're very close to perfectly elastic. And perfectly elastic, remember, means you don't lose any energy. So, I mean, eventually, they lose energy little by little, but it does last a long time. But what happens is, one by one, these collisions, this one comes in at a speed V, stops, the next one takes off with a speed V, transfers it to the next one. And so, if you have a whole bunch of them in a row, you see this one come in, bop, they all look like they stay still, and this one comes out to the side with a speed V. And that's why you can do that calculation as an elastic collision. There's a few things. Any sound, sound is energy. Any change in temperature is energy. And so a little bit of energy is lost to air friction. A little is left to deformation in the string. A little is lost to heat changes in the balls. The fact that you hear that sound when they collide means a little is lost to producing sound, but it's not very much. Any questions about that? So the problems I'm going to have you do are only plastic deformation, plastic collisions, but that's a good thing to have seen at least. That'll come up again sometime. All right, bye.